generative style of DL architecture. Can you able to recollect where we came across this generative style of deep learning architecture? Do you remember this deep learning architecture is primarily any deep learning architecture you can design, number one, as a classifier model, isn't it? As a classifier model, whether it's a binary or multi-class. Number two, you can design as a regressor model. Also, I have mentioned in one of the topic, I can design a deep learning architecture as a generative architecture. Generative architecture. What is the classification scope? What is another name for classifier? It is called as a discriminator, isn't it? Discriminator. What is the role of discriminator? It is just discriminating. It is making a decision as the whether the incoming data belongs to this class or this class. Even most of the encoder, again, I'm relating this idea to the LLM model. Suppose if you wanted to connect this idea to the LLM, it is encoder only. Most of the encoder only design, we use it for say for example, sentiment analysis and all. We try to discriminate the sentiment, whether it's a positive sentiment or a negative sentiment. Okay. So in that way, you can connect this idea to the large language model. Or named entity recognition. You wanted to classify this as a person or a city, or it is a geographical location, or it is a company name. Again, it is a classifier task. It is discriminating. Okay, which token is a person, which token is a city name, which a token is the company name. So again, encoder style of architecture. So can you try to recollect where we have seen this generative style component in the earlier topic discussion?
Sir, in the unit, there we will have two paths, contraction and extraction path.
Correct.
So
which portion?
The second portion.
Yeah, very good. Yeah, very good. So even when I was discussing this unit architecture, that time itself I mentioned we'll be discussing this expansion part again in future. I mentioned I have given an indicator during the later course of time, particularly the last two sessions, we'll be revisiting this expansion part. Actually, in the unit architecture, this contraction part work like, again, I can include that also another aspect of, isn't it? Shall I put another sub branch of this role of DL? What name I can give for that contraction part? Contraction part. What name can we give for that?
The feature extraction.
Very good. Feature extraction. See, as a discriminator model uses a final fully connected layer, okay, with certain number of hidden layer, and finally an output layer. Okay, finally there is an output layer with one hot encoding vector to discriminate what is the incoming data is. Okay, to classify what is the incoming data. If I remove this, okay, if I remove this, again, choice is yours, whether you wanted to have the feature in a two-dimensional representation of the feature or one-dimensional representation of the feature. Okay, even in this contraction part, we have the final, your input image, I think 256 by 256 we started, and final size we have brought down this to 16 cross 16, I guess. Okay, the condensed representation, 16 cross 16. If you wanted to have a two-dimensional feature representation, entire fully connected layer you can remove. Okay, so in the unit architecture, we have used the deep learning architecture as a feature extractor. Again, as a feature extractor, I can make a two subcomponent as a two-dimensional or one-dimensional. Which application we have taken as a two-dimensional? The contraction path of your unit architecture, I have used a two-dimensional. Can you recollect one of the application we have used one-dimensional representation? Because this two-dimensional also we have flattened it using a flattening layer, and we mapped this to some hidden layer. Because say for example, this after flattening, this is like a huge features. If you wanted to compress this feature as a linear combination of the weights, and maybe you can represent this with only 512 feature or even 256 feature, that is also possible, right? Because this is going to represent the raw feature, whereas you mapped onto a fully connected layer means hidden layer means, what is the meaning of this? Instead of representing your feature as a raw features, you are representing as a linear combination of weights. Okay, so this 512 vector or even this 256 vector also can be treated as a feature. So there we treat as a one-dimensional feature. Can you relate one of the application we have used this as a one-dimensional feature vector? Recently we have seen this. FaceNet. Do you remember? FaceNet, once we extracted the face region using empty CNN. Okay, the face we have passed to a pre-trained model to get the feature vector. So CNN based pre-trained model we have passed on this, and it is going to give us the one-dimensional feature vector. So that one-dimensional feature vector, we used it for the comparison purpose, isn't it? So according to the context, whether you wanted to have a two-dimensional feature representation or one-dimensional feature representation, I can use a deep learning architecture as a feature extractor. So these are all the four major roles of the design style of your deep learning architecture: as a discriminator, as a regressor, as a generative architecture, as a feature extractor. Okay, now when you look at these two guys, it looks like a bit confusing, or more or less, or they are likely to be same or not. Okay, let us have a closer look about these two guys, okay, for more clarity. Generator, feature extractor. In feature extractor, what we do, your input is an image. Okay, input is an image. Say for example, it is a 256 by 256 image. We present this to a multiple layer of CNN layers. Finally, you extract a feature in a form of a two-dimensional. In the last CNN layer output, after max pooling, you can consider this. Or you map this to a fully connected layer, and you can extract this as a one-dimensional feature or a 2D feature. This is how the architecture goes on, isn't it? Do you remember the generative architecture of the unit? The expansion path. The expansion path actually started with the 16 by 16. Okay, and then gradually we upscaled convolution 2D transpose we have used for the upscaling it. We keep on upscale this 64 by 64, then 128 by 128, and finally we have got, okay, 256 by 256 in the output. So what is the major difference? Here it is a series of convolution layer, but in the generative architecture, it is a deconvolution. You start again, this generator model I can do, the same generator model can work. Even I can start with a one-dimensional vector, possible or not. Instead of a two-dimensional, even I can have one-dimensional vector. Say for example, I have one-dimensional vector, something like this, 512. Or okay, even I can start with the one-dimensional. This one-dimensional I can reshape to two-dimensional, something like a 25 by 25, and I can upscale it to generate the whatever the size of the image I wanted to generate, I can generate. It's possible for me, isn't it? So the input size is not the constraint for the generator, because whether you even though if your input comes in a one-dimensional format, I can even easily reshape it, and I can do the convolution 2D transpose. I can generate this. Okay, so the beauty of the generator model is, okay, the beauty of the generator model is whatever you wanted to achieve finally, what you wanted to achieve finally, that you can design accordingly. Whereas in the unit architecture, the final 56 by 56 matrix should close to my target. What is the target? It is a two-dimensional target. We have set the two-dimensional target. Okay, these are all the object pixels. These are all the background pixels. Wherever my object pixels are there, they are white pixels, and the remaining are 0 pixels. Okay, so this is something like a two-dimensional one-hot encoding representation. So with the objective of this target, reference target, we have upscaled this, and your weights are being updated, or your model weights are updated in such a way that it is keep updating, your weights are being updated, and your because to upscale your image or your convolution 2D transpose, anyhow I have to operate the kernel. Okay, with a stride of true. With a stride of 2, we operate in the kernel. That means the weight of the kernel has to be updated in such a way that to produce the final output, which is similar to my target. With that notion, we have used the generator. Okay, the same generator idea, I'm going to use it as one of the component of your GAN architecture. So your generator is one of the component. Okay, that is not the only component. But but here my objective is different. Okay, the idea of the generator idea I'm going to use. Okay, the idea of the architecture of the generator architecture I'm going to use. But there I have used the generator architecture used for the semantic segmentation, because there the objective is different. But here the objective is different. Okay, that means here I have a different objective. So we with respect to any particular target, I'm not going to produce this 2D image. Okay, here my goal is something different. Okay, so here also I'm going to use the generator architecture. Okay, I'm going to start with the either I can start with a 2D or one-dimensional vector. From that, I'm going to achieve a 2D image. Okay, this is one entity. That is why it is being called as a generative. And the second entity here, we are using an adversarial. Let us try to understand. To arrive the meaning of adversarial, we have to travel a little bit more.